Hi there. It's a brand new month, it's a brand new week, and we are back with another exciting webinar today. It's great to see you all back for the third installment of our AI Explore webinar series. And whether you are a seasoned ML engineer or you are just getting into it, today's session is all about making your AI models truly production ready. So if you have ever built something you are proud of, it can be an application, a script, or an AI model. The real test is when it leaves your laptop, it leaves your dev environment and faces the wilds of production. Today, we are diving exactly into that make or break moment, optimizing, deploying, and scaling your machine learning models. It's going to be like, it works on my machine to it works at scale. So, welcome to the third episode of our AI Explore webinar series. And today's discussion area is model to production, optimizing, deploying, and scaling ML inferences. And talking about that, in case you missed it, we would like to tell you that we are the proud sponsors of NVIDIA AI Summit that's happening in Mumbai on October 24th and 25th. So do drop by our booth to learn more about the exciting things that we are doing at InfraCloud. And we also have some cutting edge demos planned. So do come and check out what we have in store and also have some fun games to test your AI skills. So if you think you are an AI wizard, you have to visit our booth and play these amazing games. Having said that, if this is the first time you're joining our webinar, do note down that this isn't the first time we are doing it. We have done a lot of webinars in the past, and especially the AI Explore series. So if you want to check out the other webinars we did in this series, we spoke about setting up your own AI lab. We also discussed about how to observe your entire AI infrastructure, and today we are going to discuss about model serving and deployment techniques. So if you want to check out any of our previous videos, all you have to do is scan the QR code that is on your screen, and it will take you to our YouTube playlist where you can access all the previous videos that we have uploaded till now. And like always, I am not the only one today. I have some guests along with me. So before I bring on the guest for today, a quick introduction about me because I spoke a lot and didn't introduce myself to all the new folks who are joining in. I'm Atul Priya Sharma, a senior developer advocate at InfraCloud, where I help build POCs and content strategy for our customers and clients to help them and their developers adopt open source and cloud native tech. I'm also a CNCF ambassador and actively involved in the community. And when I'm not doing community or content, you can find me at a restaurant trying out a new cuisine. So that's pretty much about me. And let me get on the stage the guests for today. I have Sanket and I have Aman. Hi, Aman. Hi, Sanket. Thank you so much for tuning in.
Yeah,
Yeah.
here too.
Great. So both Sanket and Aman aren't the first time guests over here. This is their second or third stint, if I am correct. And if you have seen a previous webinar, you probably know about them. But then if you're tuning in for the first time, we need to know what they are and what they do. So Sanket and Aman, why don't you go ahead and introduce yourself to our audience?
So, so I'm Sanket. I'm principal engineer at InfraCloud. I've been dabbling around AI past 1 year for past 1 year. My interest areas are AI, cloud, and distributed systems. And so when I'm not basically coding or exploring infrastructure, I mostly spend time reading, playing sports, or playing with my daughter, who is now 8 months old. So uh, that's pretty much about me. Excited to present what we have today.
Great. Thanks, Sanket. Aman, over to you.
Thanks. Hey everyone, I'm Aman, Principal Engineer at InfraCloud. My interest areas are mostly around cloud native systems. I've been working for them around 12 years now. In the last 1 or 2 years, focus is more on like AI cloud and how to add similar things in the AI cloud world. Uh, when not doing all these things, I will be either reading a book or probably watching a movie. That's it.
Interesting. So we have a voracious reader, a movie buff, and a new parent who is seeing his daughter grow. And I think that's really how an application grows as well. Your model, you start with something small and then you see it growing, learning, evolving, and then reaching to the masses. A little bit of housekeeping stuff before we, move forward. Like always, we would be taking questions from all of you. So do put in your questions, queries, suggestion in the comment box wherever you're joining in. If you're tuning in from LinkedIn, put it in the comments, and I will take the question with our guests. Or if you're joining in from YouTube or StreamYard, just put in your questions, and we would be happy to take them up. So, starting with the most basic question, what exactly is a Gen AI model? So, I'm sure all of us use AI in our day to day lives. And when you ask a question, let's say to ChatGPT, it's not just looking up an answer from a database. Instead, it is trying to understand the input that you have provided. Based on that, it tries to predict the next best response and create something in real time. And that could be text, it could be code, or even images or videos in more advanced models. So essentially speaking about what is a generative AI model? It's basically an algorithm that learns patterns from data to make predictions. So your model is typically an algorithm that is trained with a lot of data from different sources. And based on that, it learns to identify patterns to make predictions. Gen AI models are sophisticated deep learning models that, as the name suggests, generate text, image, audio, and video when given a certain instruction. So, basically, like when you provide a prompt, hey, generate an image of Mumbai skyline with Gateway of India and Taj Hotel, it actually tries to understand what you have provided. And based on the learning that it has, it'll try to generate an image about that. So it is built by feeding large amounts of data and allowing the model to learn over time and improve when it comes to predicting the outputs. And it could be, like I said, generating text, image, or videos. And there are different techniques each model employs to improve the predictions over time. And that is why if you ask one prompt, or if you give one prompt to different models, you will get different answers from each of them. And that is where the techniques with which they are built, they are trained, that is where it affects that. So now that you have a very basic and just idea of what generative AI models are and how to create and how they work to create new content, the next big question here is how do we actually use them in real world, right? I had an algorithm, I trained it with tons and petabytes of data, and the model is working, it's answering my queries. But then the real question is how do you get it to the real world audience? And that's exactly where model serving comes into play. At a very high level, it's a process that takes your trained model, the Gen AI model that you did, the ChatGPT sort of model that we discussed, from the lab to an actual production setup, making it available to folks at scale. Now, this, if you see, is a very straightforward and a very layman description that I've given. And that is why I have experts with me who actually can help define and refine this description. So over to Aman, who can help us more about model serving, what it is, how it works, why it's needed, etc., etc., etc.
Sure, sir. Yeah. If I say like the analogy that you give is exactly the one that will be required here. Basically, you have a code, you have a process. Now you have designed it, you have created your service. Now, how do you run it? And it same happens with the models as well, because ultimately models also run as a process within your computer system. So, how do you serve them? How do you make them usable? Of course, no one is going to use it like just installing it in their computer and using it as CLI. You need to create some applications on top of it, probably APIs, gRPC, whatnot. So like in the typical application world, we have three models of serving usually. There are more, but I'll just call the top three ones, which is like you have a synchronous model, you just make a request, you have an API endpoint, and you get a response. So basically, your more inference or your model is basically running in a container or let's say in any process or VM machine, and it's wrapped up by an API server. You make a request, you get the response. Now, when we create applications, sometimes interactivity becomes the prime key, and how your customers are engaged. Like you see at ChatGPT, you type in something and it doesn't give you like a response in one single shot. It will keep on typing it. That's like a streaming model. It's an interactive model. It will keep you data, and you feel like someone is really writing it. So that's what the streaming model does. You kind of stream the content back to it. You can have a batch data, and you can even put a stream layer in front of it, and you can even handle the load as well. And lastly, the batch model, where you don't care about the latency, but what you care about is that your hardware or whatever you're using is used to its max peak. And that's where you can use the batch models, because throughput is your main concern rather than throughput or utilization of your hardware is your primary concern rather than the end user latencies. So you can basically put all your data as a bunch of sheet within a sheet or any other file formats or any other data formats, and you just submit it to a model, and then model will process it. In these cases, this utilization of GPUs and all these things is pretty high, because it doesn't need to respond immediately, but it needs to be very efficient to process all the data. Yeah. Now, when we talk about serving layer, there are always two components in the inference side of LLMs or GenAI models. Now, we have a typical server thing where you put your code and you put it behind a server, or you put it along with the server, and then it can serve the request, whatever is coming in front of it. But when it comes to LLMs, there is also called an engine thing. Now, what the purpose of engine is, you have to do certain optimizations. Like, let's say if your model is not performing to your speed, it is not utilizing the hardware properly. You're seeing memory issues, you're seeing CPU utilization, GPU utilization issues. Those kinds of tunings are basically done at engine level. And when it comes to your serving side, where you have your customers and where you have to make sure that you're able to handle, let's say, millions of requests per second, and how are you performing and scaling based on that, that is the part where server comes in. So if you see, these are the two components that will always remain there. There are multiple frameworks to do that as well, like VLM, Ray. Some falls in the engine category, some falls in the server category only, or some falls in both. Like Kubeflow can work as a framework, and it can tie it to multiple frameworks, multiple servers, and you can just deploy it. Same as Racer, but TGI, it is also an engine as well as server in itself. So you can utilize it only to do that. Same with NVIDIA Triton. It's a server, but they have their own engines like TensorRT LLM, or you can even use VLLM with the Triton inference server. So you can combine these things, or you can use just one. So that's where these frameworks help in doing all these activities.
Yeah, sorry, I was on mute. Interesting insight. So I think, model serving involves a lot of components, like you rightly spoke about, talking about the backend and, server capabilities, right? And now that we understood or got an idea into how models are served into production, the actual real world challenge is making sure how they can handle the real world demand, right? So just imagine that you are giving a prompt to a chat GPT or a Claude or a Gemini, and imagine it taking more than 5 seconds or 10 seconds to respond to your query, right? You would really be like, hey, what's going wrong? Why the hell are you taking so much time to, respond to my query? Now, from a user's perspective, that is latency. That's just the tip of the iceberg, if I can say. When it comes to the performance of the model. So as more and more users interact with these models, whether it's generating text, queries, or making predictions, we need to have strategies in place to make sure that these are running smoothly and efficiently, even at scale. When these models are responding to concurrent users who are, located at different geographies, have different network requirements, different devices, you want your models to be working perfectly well. And that is where we focus on a lot of optimization techniques, where we try to focus on how we can best utilize the hardware that we have and provide the best throughput or the experience to the end users who are using it, right? So in this specific section, we would be looking at a few techniques that will help optimize the models that you have in place so that you can take full advantage of your infrastructure and other things that are associated with that. So, Aman, over to you again for a deep dive into model optimizations.
Sure. First of all, let's look at why you actually need optimization. I think you already summarized it, but key points, like you mentioned, latency. It is the first thing where customer notices it, and then it becomes a pain for everyone to troubleshoot and do it, because that's where your key product performance and everything is measured. Now, when we talk about optimizations, one thing I would like to call out is there is also a thing called tuning the models. That is also considered as part of optimization. But today we'll be focusing more on, let's say, when you have tuned your model already. You have done LoRa, QLoRa, and all these techniques, and you have fine tuned it. You have your own context and everything added to it. Now, once you have that model, now you need to deploy it into your production systems. How do you do that? So that's where we will be focusing more on the optimization technique that we are covering today. Now, if you start with it, the first one I would call it is quantization. Now, quantization is a very simple. I mean, if we have to explain it like a simple one, like you have a precision of 32 bits, you reduce it to 8 bits. It sounds very simple when you read it in that way, but yeah, it is actually it has many things behind it. You can run it smoothly with any of these frameworks. All of these frameworks that I spoke about earlier, they support it. It's just one command that you have to fire. You have to understand what your existing data type is and what data type you want to reach to. But what you need to understand here is you're not training a model. It is a trained model. It's a model that is ready for inference. And now you're doing a quantization. So you're not doing on all the data. You're only doing on the parameters and weights, right? What can be the side effects of it? You can lose certain precision because you are reducing the your model precision, like FP16 to getting to 8 int 8 or something like that, int 8 to int 4, or using mixed precisions. In all these models, you will lose certain precisions when you make calls to your servers or generate outputs out of it. But in many cases, we have noticed that it doesn't matter a lot because unless and until you're really running or building something that needs that very granular precisions, then probably yes, you need to run model as it is. It was trained on whatever the memory data types were. But if not, in many of the cases like translation, like you're building a small app within for your organization, you're building for a small customer base for a very dedicated case, you can do that, and it really helps you to load your model onto the hardware. You always don't need like a bigger hardware or bigger GPUs and all those sizes. Like we run Llama 3 8 billion model on the RTX 4090, which is basically a 24 GB machine. We quantize it a bit and we can easily run multiple replicas of it, and we can test it, validate it, create applications on top of it and whatnot. So that's the advantage of using quantization. Use it anywhere on your local system. If it has a GPU, use it on the smaller system. You always don't need like H100 and all those buzz GPUs. Yeah. Pruning is very interesting one because here uh, what you're basically doing is you are taking away the parameters that are not kind of useful to you. Now, this is slightly complex because you need to understand what parameters you are using, what not. Now, it sounds like you have to choose, but the way it works or the libraries are currently doing it is basically weights are basically the numbers. You can consider it like something like 1.1, 1.5, 2, whatnot. These kinds of decimal numbers, etc. Like now, it will go in and check like if the probability is very near to zero for that particular weight or parameter, then probably it might not be used in entire model quite often. So it will take out those parameters and remove it for you. So all you do is you take a big model, you run it through a pruning utility. It will check like whatever weights or parameters that have a very low bias or very low probability. It will remove them. What it will do, it will reduce your model size. Again, the benefits like quantization. You can use that model, small models on any hardware. You can deploy it. You can scale it well. Your inference speed would be better, and your precisions, you're targeting a specific thing because you have already assumed that you're not using those edge cases and you have removed them. So your use case should also be very targeted in these cases. Uh, Distillation, again, it sounds very much like pruning. It's again one of the model compression techniques. But the reason it is very interesting is you take a very big model, and nowadays we see like foundation models are getting bigger and bigger. But they're also consuming a lot of data, like sometimes the entire internet and whatnot. And the application that you might be building is not relevant to that. Like you don't need that entire internet data, but you still need that capability of generative AI or LLM models. Now, how can you do that? Probably choose a better model and create a sub model out of it. So if you see the diagram, it's again saying like a teacher model, which could be any of the foundational models that are out there. Now you target your use case. Let's say you're only targeting translation. That's it. And that too within a specific language. Then you can just carve out a small student model out of it and use that model. That model will be literally a very low size and it is still capable as the foundational model. No changes are made to the foundational model in this case. Only a new student model is created, a smaller model. And that can even be fine-tuned on your specific data and it will still perform as good as the feature model in the optimization and performance wise. Now, this is about KV caching. It is very much to the all these transformer based models, LLMs that we are seeing currently, all these bigger foundational models. Now, usually you have like different memories in your system, right? You have a RAM. Then when it comes to GPU has also multiple RAM, multiple memory systems, right? It has a small memory that is very close to your cores, CUDA cores or the streaming multiprocessors. It's like a cache. Then it has a bigger memory piece, which is basically your high bandwidth memory, and that's called like VRAM. And it is the one where all when you load a model, all your parameters and everything will be loaded. Now, when you make a query, many of the times the nature of LLM is it's an autoregressive. You ask a question, then it will generate a word, then it will attach to your original sentence, and then it will again generate the next word, right? So there's a lot of reutilization of the your initial query, and that's where these KV caching strategies comes into play. Because if you load the entire parameters all the time, the queries, the values, the weights, and everything, your memory will become full very soon, and you'll not be able to utilize the system to its performance. What will happen is a lot of data will go to the disk, and then you have to read it from disk if it is convenient. Now, in the KV caching strategies, again, there are multiple options you can use, and it is also baked into the different servers, engines that we are using. So it comes down to your attention mechanism tuning. One way to call it is like you must have heard about VLLM. It uses paged attention. What it does is because it just reads some data from the memory and some from the whatever is required currently, it creates the blocks for that and it uses those. Right, you have group query attentions, multi-query attentions. Basically, you group your query because your query is not changing. Right, once you ask the question, that's the question. It is what it is, and when the output are generated in an auto-regressive manner, it keeps appending to your query. So whatever the probabilities or weights are calculated for them, or the biases are calculated from them in the transformer model, that will not change very much. So it kind of caches them and use it into different group queries or different multiple queries. And that's where you achieve a good optimization on the key value cache that you use. So you can use your bandwidth, entire memory bandwidth, or entire memory to a very efficient way.
Thanks, Aman, for those insights on various optimization techniques. So, if you're tuning in right now, we were discussing model optimization techniques, and Aman took us through to various techniques. And if you have been here till right from the beginning, if you have any queries, please feel free to drop them in the comments as well. So, Aman, while I was listening to you, again, I'm not an expert in AI. But then there were a lot of things that I could relate to when it comes to, even deploying non-AI workloads as well. These are, I think, universally accepted, discussion or, strategies that we involve to improve the, performance of our applications. Like obviously you spoke about caching mechanism, and then you group your queries, send it to a server, in a traditional application. Now, one thing that I also realized when you spoke about quantization is, when you are, let's say, reducing the number of, let's say, features or basically going down from 32-bit to an 8-bit, you essentially lose data in that process, and that actually affects your precision as well. But then it reduces the size of your model, right? So even if I have a GPU with a lower, memory footprint, I can deploy the model into that. Now, that's where I think it would be very critical to find the right balance of how much you want to quantize it, and what is the size you want, because I'm sure that is going to affect the eventual performance of the model that that you deploy. Uh, so moving on, I think when you spoke about various different techniques, and I'm sure this would be a question to all our viewers as well. That hey, I mean, you spoke about various techniques and various ways to optimize the model, but then which one should I choose? I mean, should I, let's say I'm building something, do I need to go ahead with quantization, remove the features, reduce it, and put it, or should I prefer something more advanced, let's say like a KV caching technique, or should I use all of them? So, what are your thoughts on it? How are you going to help such users decide that what's the right model for them to use, or a process to decide what model to use?
Sure. Yeah. And you're aware that it could be like a selection of one of these, which one is the best, and or if I say it could be even, you can use all of these. So what I'll show you now is like a sample flow. The application that I'm assuming here is like someone wants to build a translation app that needs to run in a mobile. All the purpose that it has is just to do a translation, and that too can be even for a specific language. That's it, right? Now, like I said, you can start with a real original Llama model, like a 65 billion, because it's performant, it covers a lot of data, and has all the different edge cases already feed into it and whatnot. So we started with that, and we can do a model distillation. Like I said, you can create a small student model out of it, and that's what we'll be doing in the model distillation phase, right? So now we have a smaller model, which is just around what 7 billion parameters, and that's it, because we are only and only targeting the translation use cases. Now that's good, but now we notice that again there are a lot of parameters that are not adding any value to it. So we can get into the pruning part because still with 7 billion, our size is still very high and it will not run on the mobile very efficiently. So we did pruning and we even reduce it to the more smaller numbers. And let's say now we get to the 5 billion parameters. Uh, why? Because we are just removing the parameters of weights that are completely of no use. They are just adding a very small edge cases and all those things. And probably our app is a very specific translation based app. That's it. All that done now is a final step where I have to decide what memory I have and what kind of size I have in my mobile and all those things. And I still feel that I will not be able to fit a 5 billion model. So I'll go to the quantization. I'll target quantization, and let's say I tried with 8-bit quantizations. I tested it, and all the cases are working fine that we are targeting. That's what, and now that takes it to a very small number, which can even fit into your 2 GB mobile RAM or a VRAM. If you have like a GPU VRAM out there, you can use that even that. So that's how you can even use all this. This is of course a sample flow in production, or in your case in actual scenarios. It might be different. The models will be different. You might have to test it each and every stage. You did a distillation, you test your student model again. Is it performant or not? You did pruning, you have to test for those every edge cases that you feel your app can have. Same with quantization. You need to be sure that you're not hitting those edge cases where it loses the precision. You're not actually opening the doors. And in those cases, you might not be able to use quantization. You have to set at 5 billion and then make your hardware accordingly for that. So that's how you can say all things can be used. And last layer is KV caching. When it comes to engines, this is the technique everyone should definitely use. Many of the models already have it. Many of the servers already do the best KV caching mechanisms. Like if you use VLM, they already have it inbuilt inside that. Same with TGI, they also have their attention mechanism modules that are already enabled. So that comes usually with the engines and servers. But you can again, if you want to tune more, get to the last mile, you can definitely do those KV caching strategies as well.
This is a really interesting workflow, Aman, that you have shared. I mean, I cannot imagine having a 65 billion parameter running on, my mobile device as well, by following all these techniques. So for anyone, if you're watching this, I think this framework will give you a very good idea of how you can take a parent model and then do all the processes of optimizing your model and then eventually making it fit enough to run on different devices with smaller footprint, have KV caching mechanisms to improve the performance. So this is what you need to, focus on whenever you are having a model and, you are performing optimization. And I think that's the right time to take a question that we have from Vinayak, which I'm going to put it on screen. So Vinayak Shinde asked us, what is the process to carry out pruning or distillation, and are there any tools to perform any of these activities?
Okay. So many of the servers and engines that we mentioned, they already has a utility inbuilt into that. So these are like probably a Python module, a command that you can just trigger and execute it. Distillation has again like distillation pruning both have like different model. Like there is fast GPT. There are again certain frameworks that have been designed specifically to them. So you have to choose one that fits your case well. And sometimes it might need more compute because when you're doing a distillation, you're taking a big model and then training out a small model out of it. So you might need for a certain period of time a high amount of compute. So yeah, based on that, you have to choose your tools and utilities, but you don't have to write anything custom for it. Most of these popular framework servers, they already have the utilities inbuilt into that for these things.
Great. Thanks, Aman. So I think, Vinayak, in short, the answer is most of the tools, that we spoke about, the servers, have these capabilities inbuilt, and you can just use them and probably change some configuration settings based on your requirements, and you should be good to go. Thanks so much for that question. And then we are moving on with our discussion. So at this point, we have optimized our models, right? We got it down from 65 billion to, let's say, a 2 billion parameter model, which is ready to be deployed on a mobile device. But when it comes to real world scenarios, we spoke about concurrent users, we spoke about a lot of load that is being generated at one particular time. And that is where you want your model to scale based on the requests that come in. And it's not as easy as putting a load balancer and saying, hey, diverge the traffic to, the 10 models that I have, which is deployed on 10 different machines, because that's not quite feasible for a lot of reasons. So moving on to the next section, we would be discussing about a lot of parallelism and scaling techniques that are involved to make your optimized models to reach the real world folks and give them a better experience. So Aman, why don't you tell us what is the need of parallelism?
Sure. Like you said, you have your everything ready. Now is the time when you actually deploy it. And if you have been following like the cloud native world from last 8-10 years, it is the big thing that everyone is doing. How do you auto scale? How do you make handle the loads? And that's where cloud shines. You can provision nodes quickly. You can get replicas and whatnot. Now, when it comes to models, because we already see that they are of big sizes, you need bigger hardware. Uh, now, does that same thing apply over here? Is what parallelism comes into, because it might happen that your model might not fit even in your hardware. So, what is the meaning of then the parallelism? Are you taking the data and spreading? Are you taking the model and spreading it on a different system? So that is one thing you will see. Now, even the data sets can be high, or your model is small, fine, but your data set is high. Like I said about the batch workloads, right? You're processing millions of records. You're doing inferencing on millions of records, not like ChatGPT. You're asking one question at a time, and you might be a user who process multiple queries at a single time. And that's where you have to again have a replicated model. Like we have containers replicated across different nodes. Same way can we will be able to do the inference as well. So that is what inference parallelism and scaling targets. Yeah. I think the first one and the most relatable one in the normal world is data parallelism. It's like having one model and running replicated versions of it. Here, you do the fine tuning or you do the all the optimizations on your data that you insert to those models. So let's say I was talking about the batch. So I have a bunch of rows, bunch of records. Now I have to process it, but I have even enough hardware that I can run replicated instances of my model. So I can chunk my data and pass it on to a different instances. In that way, the throughput of each server will become good because they are processing only on the data size that they can handle. And for me, again, I'm doing a parallel processing because I've just passed on the data to multiple servers because I had hardware, and that's where I can utilize on the both sides. My inference will be good, my throughput utilization of the hardware will be good, and response will be good. It might not be make sense to doing for like interactive sessions because there it's just about the load that you are getting. Right? You can relate to that like ChatGPT, like multiple users are making a request at the same time. Millions of requests are coming in, so you can spread it out. You can maintain those sessions within one server so that context is not lost and all those things. But yeah, that in that way you can use this data parallelism. Now, tensor parallelism, it is about the models and the networks. So all these models are basically based off like neural networks, right? So you have different tensors that are basically kind of you can think of it like a brain or memories kind of it, right? For within a model. Now in tensor parallelism, you can basically split a model. Like I was talking earlier, you can split a model and then put that model pieces into different GPUs. So it could be within your one node, it could be across your multiple nodes. Now when what will happen is, let's say I have a one model and I did the tensor parallelism, I enabled it, then certain tensors will be loaded into certain GPU, certain other tensors will be loaded into that. That split happens very smartly. It's not like random one. Otherwise, data will keep running here and there. So the split happens very smartly and handled by all these optimization engines only, server engines basically. Now, where you will benefit from it? Basically, you are split if you want to run a bigger model and you don't have like one GPU can fit into it, then you can use multiple GPUs. But here the limitation that you will hit is you need to have very high performance networks as well. So let's say if you're using only one box, using something like NVLink would be really shiny, really shiny. Within two GPU machines, you could have high-speed interconnect GPU networks because your data might flow from after processing from one GPU, certain tensors process it. Now it will move on to the next GPU. So you have to have that high performance network. Otherwise, network will become a bottleneck for you.
Absolutely. I think Aman is just recapping what we discussed in our previous webinars is the importance of network. A lot of us, when we talk about AI, it's all GPU, 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 maybe a little bit around power, but the fast network and fast storage are something which is very critical when it comes to working with models. So tensor parallelism, you need a high bandwidth network with you along on the systems that you are working on. Moving on to the next one.
Pipeline parallelism, it might sound very similar to the tensor one, but the change is so if I have to take an analogy, you might have like sequential jobs in the normal world. In the cloud native world, we have seen like jobs that are being run. Like you have a certain workflows that you create. Basically, execute this and execute that. Then go if the result is this, then go into that particular portion of the code. Okay. Now, when we talk about pipeline parallelism, it's almost same. If you are processing something which is sequential, right? You know that certain things need to be processed first, and then it can be passed on to the other layer. Then pipeline parallelism is really good for you. You can split the model into the sequential stages. Let's say you did certain n numbers of layers in one first GPU, then you add the other layers in the next one because you know that the way things you are going to do that will be purely a sequential operation, and that's where you can again leverage the multiple GPUs. But again, like I said in the tensor parallelism, whenever you go beyond one GPU, network becomes a bottleneck. It's not too much in data parallelism because it's a replicated mode, so no GPU to GPU communication happens. But when you talk about pipeline and tensor parallelism, a lot of GPU to GPU communication will happen, and that's where you need to have a good high speed network between your GPUs, be it within one box, be it across the boxes. And the last one is expert parallelism. This is more of like you might have seen a lot of new models are coming up which are called as like mixture of expert. What it does is basically it has uses different technique where the model is not just one single thing where you get like a one model and you make any questions to it, then it will process the entire model for it. It has enabled certain networks like basically it has internally multiple experts for different areas, right? It could be anything like it could be based on like let's say translation, language translation, all those things, and then it could be certain around like games, novels, and whatnot. Now you can enable only the things that you need, or it could be even multimodal. Like let's say you enabled text, and then there is certain for video part, but you don't need it. You don't enable that. That's where expert parallelism comes in. You might have to use even the models that actually have those multiple experts is the precursor to it. But what it does is you get a model, you make queries. It will only and only turn on the exports or neural networks that are needed to process that part. It will not do the other things. So it will not load the entire models, 10 different models, and all those things. You can still have a model that can do multiple things, but you will only be enabling the one that you need.
Yes. So I think, we looked at four different parallelism techniques to, serve your models to the real world solutions. And I think, again, a lot of questions that need to be answered here, right? Let's say if I have multiple GPUs, but then that's where my network becomes a bottleneck. But then if I don't have multiple GPUs, that's where I look at something like a data parallelism. So again, the, overarching question here is, which technique should I use to, serve my model in a better way so that my entire resource is utilized perfectly. So I think Aman again has a very detailed and interesting sample flow that will help all of us understand how to choose the technique which suits our requirement best, or how to choose between multiple techniques to get the best output for the process that you are, going ahead with. So Aman, over to you.
Yeah, and whenever we heard about parallelism scaling, it looked very tempting. That why not use it, increase the performance and whatnot. But yeah, we have generated this small flow diagram which is very basic one, but what it targets is like just placing you where which kind of parallelism technique might be a good choice for you. It can be a starter. You can again deep dive and go into making decisions. But let's say you start with it, and if your model size exceeds your single device memory. So I was talking earlier that we were using RTX 4090, which is 24 GB. So we are boxed, like beyond 24 GB, we cannot go. Now, if you choose any model that is basically more than this size, then we need to have certain parallelism. Now, within that, we need to understand, is my model sequential? Like I was saying earlier, like is it that the data that I will pass in, it will be processed in a stages? Then it's fine. I'll straightforward go with pipeline parallelism. But no, if it is not like that, it can go into any layers and it can do that, then probably tensor parallelism works better for me. In that way, I can use more of my hardware utilization and increase that. Now, when it comes to like the model size doesn't exceed single device memory. It's good. It can fit into that box. Now we are choosing small models or whatever. I have a H100, let's say, and a big memory. I can fit the model into it. Then what is it that decides when I need a parallelism? So there it becomes important. Like, what is your input batches? Are you making just one queries and you know that your customer load might not be more than 100 requests per second? It can easily handle that. It can generate even the KV caches and all those things for it. Then you probably don't need anything. You can even run a single device inference. Your diverse input types or tasks are okay, and you run a single device inference, right? But let's say you have a big batches, you are processing billions of multiple order, millions of orders in a day, you're generating inference on top of this, then you need data parallelism. That is the path that you have to go. Or if you are processing multiple different diverse data types, you have text, you have videos and whatnot, then you can go and leverage expert parallelism. Expert parallelism will, like I said, will take your inputs, understand what layer need to be activated, what expert needs to be activated, and will only activate that. So it can still fit in your boxes, and on demand, it will turn on the neural networks of experts that are required.
Right. So if you want to take a screenshot of this, you can, but we are recording this, so you can anytime tune into our YouTube playlist to watch this webinar again and go through whatever Aman has discussed. But then again, this is a very good blueprint for all of us, who are working in this area and want to or are confused between, what are a better parallelism technique that they should be applying. So thank you, Aman, for taking us through that. And thank you, Aman, also for giving us in-depth insights on, quantization techniques to optimization as well as parallelism. And I think it's great that we could cram in such huge amounts of information in such crisp way. I'm sure all of you who have joined in and watched this live, you can go back and now you know what KV caching is, or you know how quantization can affect you, and even the flow diagrams that Aman had shared. So thank you so much, Aman, for that good theory lesson to all of us. And now I think it's the most exciting part where we want to implement what we have learned, right? So, Aman has been teaching me, especially for the last week, about all these processes. So I have had got some idea, and Sanket, who is the master engineer here, has taken those learnings and implemented it on the models that we have on our AI lab. So now I'll throw it to Sanket, who will take us through the demo and show us how you can actually implement some of these techniques to optimize your models and then serve them. So Sanket, the stage is all yours.
So, so we can do a quick walkthrough of the. So I think we have introduced our lab in last webinars. So essentially, right now we have like let's say 3 machines with GPUs, RTX 4090 cards, and then so this is more like a miniature lab that we have built out, and then so if you're like interested in knowing more details about like all the lab, etc., definitely go through our previous webinars, I would say. Uh, and so now, so the AI stack that we have set up on this lab as of now is so we have designed our own charts and etc. to deploy the model, so which we'll be like demoing today. So this is more the entire stack which is shown in the slide is more like a lower layers that we have built so far, right? Okay, so I'll share my screen and quickly walk through the like demo now.
Yes, moving on to the screen, getting Sanket's screen
Okay.
online. Yes.
Okay.
Sanket, can you zoom in a little bit so that it becomes easier for our viewers to read what it is? Yes, that's
Yeah.
perfect.
Okay. So effectively, like let's say when you want to host a model, right? First, you want to get the weights of that model. So for example, let's consider a sample model. I have Llama 3.2 1B model. And you can see like if you explore the weights and all, you can see so typically you will see like safe tensors files in that particular model repo, and you have to download these model weights. So as I mentioned, we use NFS. So my typical step is to just download the model weights. So I can say, let's say, this is the command which I typically fire. So Hugging Face, download model ID, and I'll download the model weights, right? So since I've already downloaded weights, I can see those are available in my NFS. I can also see what all models I have like downloaded in the past. So you can see a bunch of models which I've downloaded and tried out. So let's say uh, I want to quickly launch this model, right? So I think we have introduced our AI stack. So let's say I want to launch a model. Okay, so I want to launch a model 3.21b instruct. So this is the UI that we have built on top of our AI stack. So this is a wrapper UI. So this helps me in launching the model quickly. So I'll quickly select like node where I want to launch, and I'm, let's say, using VLLM to launch the model. I'm creating an inference endpoint. So what this does in the backend is we are just launching like a Helm chart, uh, which deploys this model. Okay, so this takes a bit of time to launch the model. Meanwhile, we can also see all the GPU nodes that we have, and we have observability also on them. I can see, let's see. Okay, so this, so I'm just checking for the pod that we just launched. So let's say this model is getting launched. Yeah, I see the pod VLLM pod is launched with the model weights, and it's just processing further. So it will load the model weights, etc. Okay, I can see now the endpoints are accessible for the model. We can quickly fire, let's say, models API on VLLM and then just see, okay, our model is available. The model which we just downloaded and launched. So it's 3.21b instruct model, right? We can quickly invoke this model. So I have a handy command to try out. Okay, the screen is full. Okay. So I'll call a completions API. So most of the time, if you have tried like OpenAI APIs or something like that, so this is a standard endpoint that OpenAI provides, or any model which is sort of an instruct model, it provides these APIs. So if I call, so what I'm doing here is I'm mentioning the model. Then these are the so this is like a prompt, system prompt, and then this is my query. What is deep learning? And I've mentioned, okay, you can use like max tokens 256. So when I execute this, so I should like receive a response. Okay. So I should receive a response. So let me try like once here. I have.
So we have our demo gods trying to play their part in the live demo.
Okay. Yeah. So
Yeah.
I got the response. So mostly I think something was incorrect in the payload that I sent. So I see, like, for example, my query was what is deep learning, right? I received some response from the model that we have hosted. So yeah, I mean, so 3.1b is very small model, but I've already created few models for myself just for the demo purpose. So let's say I have few more models which I had hosted. So this is the UI where I see which all models I have hosted. So I have 3.8, uh, 3.18b instruct model, so which I have hosted on one of the node. It's hosted with VLLM. And then there is also one more model which is using AWQ, which is activation. Uh, activation aware weight quantization sort of. Uh, so we'll compare like both of these two models, just sort of run a quick benchmark and then see, what kind of performance we get from these two models. So let's say I have, so let's first try out 3.18b instruct model. So what I would do is, let's say I have a benchmark script, which I will run over that model. Okay, let me quickly copy the commands. Meanwhile, I'll also set up some dashboards. So right now we see I haven't made any request to this model. So most of the graphs that I have are empty. So I don't see. So what I'm going to do is, let's say I'm making like 200 requests to the model with concurrency of 10, and then there are certain additional parameters that we are mentioning. Okay, so I see the requests are getting made. So typically what happens is once you start making requests, we have Grafana dashboard through which we monitor these metrics, and also we have embedded Grafana dashboard panels in this UI, so we can quickly monitor some of the metrics, etc.
And a shameless plug there, we did a webinar only dedicated to
Yeah,
observing an AI platform. So you can do check that out. And we have some responses here on our panels.
yeah. So as I'm making requests to the model, I can see the throughput is rising sort of, and I can see, let's say, current throughput is around 69 token per second, right? And then there are a couple of additional metrics that I can see. What is the end-to-end latency that user sees for a particular request? And these are helpful metrics: time to first token latency, and then time per output token latency. So these are the key metrics which you watch, let's say, when we are benchmarking a particular model, right? So these help you in identifying how your model is performing, how it is serving to your users, etc.
And while Sanket
Uh,
is doing that, if you have any questions regarding the demo, please feel free to drop them in the comment section.
yeah. So yeah, my charts are becoming more colorful now as we are sending more requests. So yeah, the throughput is also rising as I make more requests. So yeah, I mean, right now, let's say we are getting around 400 token per second throughput here, right? And if I go to another model, so this is a quantized model, like quantized version of the same model that we just tried out. Maybe what we can do is we can also make requests to this model and then see how it goes. So we'll stop probably the request. Okay. So these are the high level statistics that we have got from our benchmarking results. So we some like, so this is more like a end-to-end throughput that client has seen, which is around 50 token per second. And these are some stats that we see, like Okay, time to first token. Then there's a latency. What is the latency that end user has seen? And then there are metrics which we have seen from our uh, dashboard per se, right? Now let's try another model, which is quantized model. So, okay, let me start benchmark for this. Yeah, so dashboard empty. Okay, so my requests are flowing.
And we are waiting for more colorful charts to come up on the panel so that
Yeah.
we know everything's working. Once again, if you have any questions, do put in the comments. There is one which I'll probably take up once Sanket is done with the demo.
So meanwhile, I can also I'm quickly like walking as we make more requests to the models, right? We can see the temperature rises for particular GPUs. Then power consumption also rises, and yeah, you can see like probably the memory consumption for those particular GPUs with wherever the models are hosted. So this essentially helps you in understanding how your resources are getting utilized. Okay, so I see like bit more metrics coming in. Okay, yeah. So as we see here, probably the throughput is almost double or twice of what we got earlier. So earlier we got around like 50 token per second from users' point of view, and we are almost getting like a twice of the throughput that we got. So since I'm using like a quantized model, which probably does a better job in computations, whereas we might be losing some sort of accuracy in the model, but we get more tokens per second, and we are able to serve, let's say, more users when we are using quantization. So yeah, I think this pretty much covers. So we can see here like almost we saw around like 400 tokens per second, right? In the other chart here we see throughput going around 600 token per second, and sometimes I've seen it going around, let's say, 1,000 or 1,500 token per second as I do tweak some things on the model side. So yeah, that's pretty much what I wanted to cover. Over to you, Atul.
Great. Thanks so much again, Sanket, for giving us that demo. I do have a question in the comments from one of our guests, but then I will take the liberty of asking my question first to you. So I do understand that when you are doing any sort of optimization, there is a lot of testing sort of involved to identify the exact thing, the exact output that you need. You try a lot of things and then you get the desired output. So typically, I want to get some idea from you. How is this process actually done? When you are doing the optimization process, are there tools that are available that help you throw some data to it? You get output and you realize, okay, hey, this is not right. Maybe I need to quantize it better or lose something. Maybe some light on that process. How do you really optimize or maybe test how the model is performing?
So first thing when I'm trying out the model, right? First I'll check if do I have enough resources to run that model. Means like GPU memory. Do I have enough GPU memory, and then even system resources, if those are enough or not, right? If not, then probably I'll follow the flow which Aman has mentioned. We have to do quantization, etc. Now, when you have to do quantization, definitely the tools are there. So like we are using, let's say, TGI or VLLM, etc. You can mention the quantization parameters at runtime. Like if you're just doing, so there are different quantization techniques typically used, which are used. So the one popular one is bits and bytes, which isn't, you just mention, okay, I want to load model in 4-bit, int4 or int8 data type. So in that case, this can pretty much done at runtime. And if you want to use techniques like AWQ, which is active weight aware quantization, or there are also some methods like GPTQ, uh, or now this is a popular framework GGUF. So these are different quantization techniques, and if you have to do like these quantization techniques, so then probably there are different methods depending on which quantization technique you are using. But most of the time you would find these models quantized by some of the open source folks, and they once the quantization is done, they will host or post these models on Hugging Face. So if you just search by model name and then just put prefix or suffix like GPTQ or let's say AWQ, you'll find weights for the quantized model. If you don't find, then definitely there is a process to do it. Let's say if you are doing like Llama 70B model quantization with AWQ. So in that case, probably you will need some data set and then one GPU. And then probably it will take like 2 hours to get your model quantized with, let's say, within AWQ. Or GPTQ also takes a bit of time. But let's say if you're just doing loading a model in a lower size, then you don't need that much time. You can pretty much do quantization at runtime. So depending on what kind of performance you're looking for, and uh, you know uh, how much memory and CPU resources you can give to model hosting, you have to consider all these aspects and then host your model accordingly. And of course, once you have hosted the model, you sort of run benchmarking, you monitor all the metrics that we just saw, and then also you have to monitor all the hardware resources that you're giving to your uh, model.
Interesting. I think, Sanket, you really provided a hack, if that's the right word, for people to look for optimized models. As Sanket pointed out, you can go to Hugging Face, type a model name, and put a suffix as AWQ, if I am correct, if I heard that right, and then
Yeah.
GGU. These are the very popular optimization techniques. So if you're on Hugging Face, just search for the model with this suffix and you can get the optimized model that you can use readily. Or if you want to optimize, you can very well take these techniques, deploy it on your hardware and then optimize the process. So thanks, Sanket, for that. And I think, David, this was pretty much your question as well, where you asked about how and where did you perform the quantization technique, and could you elaborate a bit more on the process? So that is what exactly David asked, and I think, Sanket, you answered a part of the question what David had asked. So I hope, David, Sanket answers your question as well. And if you all have any further questions, please put in the comments, as we are at the very end of our discussion today. Uh, Also, we would be doing these webinars again. We try to do them very frequently and in a responsive manner. So you can subscribe to our upcoming webinars. All you have to do is scan this QR code, and you would be updated of whatever is happening and whatever is being planned for this. Also, the UI that Sanket showed that we are using to interact with our AI infrastructure that we have deployed, we would be having a glimpse of that, or maybe an advanced version of it, at the AI Summit in Mumbai. So if you're coming to AI Summit, do drop by the InfraCloud booth to get a first-hand feel of how we built the entire stack, as well as the layer on top of it that helps you to interact with the entire system that you have actually deployed. With that, I don't see any questions, so we come to the end of today's webinar. Thank you all for joining in for today's session, especially Sanket and Aman for giving us those insightful ideas on how we can optimize our models and then deploy them. So we covered a lot of ground today, from understanding Gen AI models to serving them in production to optimizing them and scaling with parallelism. The demo actually showed you how these techniques come to life. And with blueprints and flow diagrams that Aman shared, you now have a clear path to implement these strategies in your system. And remember, like Sanket said, optimizing and scaling your model is not just about the performance. It's also about ensuring that your AI models can meet the real world demands efficiently and cost effectively. So that is where you need to figure out the right balance. And whether you are just getting started or scaling up, the tools and methods that we have covered today will help you take your model from theory to production. So thank you again for all of you for joining in. I hope you had a great webinar and looking forward to seeing you again in our upcoming edition. So have a great day and thank you once again.